finished running the code, right? We finished running the code and somehow it took 35 seconds. So that's amazing because all we did was change just function calls for .log and replace it with .add, where they were called the most often. And we got a very significant improvement in the runtime without changing any of our logic. So inside this, what we did was we changed .log to .add, and the logic didn't change, but we have a 3 times speed up. And 30 seconds to run a code is not too bad. Of course, we can do better, but it's not bad at all. Okay, for the amount of effort that we put in. So anyway, previously, if we run, we should check. We should save this and put it inside. This was over here, so let's just put it together, right? So put it over here. And then maybe let's just run this with the profiling one more time and see where we should focus on from here. Since we're doing this, we might as well just go to any of the other inefficient calls and see whether we can improve the code. Right, so obviously here we can do the same, I think. Since we're accessing a scalar, we can do the same for here. So at every point where we are accessing a scalar value, we should just replace it with .add, and we have no problem with that, as long as we're not accessing a row. So we just make changes, and they should make it even faster than the code before. So I think that's pretty much it, right? So this is also running .add, and inside, actually, we should kind of do the search here. We can do .log, and then we can look for any places that we can see that all of this are calling scalars. So except for this one. So this one is printing a row. Okay, but this one is inside the old code. So let's just look inside the new code. Right, so except for the files inside the old code where we're accessing a row, we are always accessing scalar. So we can replace this 2 positions with that. So that should be no problem. Right. We can replace it with this. And the rest of that. So we basically refactored our code so that we use the appropriate function call at the appropriate place. And then we can run our statistics file again and see how to further improve our code from here. Okay, and we can just ignore this line because this statement is not accurate, because when we are doing the function profiling, there will be an overhead. So when we are profiling the code, it will always take longer than without the profiling. So the thing we wanted to do was to basically just get our function call and then compare it to our previous performance. So we can check this. So this is our first profiling, and this is after we changed the function calls. So as you can see that the percentage of time that was originally spent inside this function, we're now saving about 20 seconds, and then we saved about 10 seconds. We're saving a significant amount of time. These are all from the same function call. So we're saving a significant amount of time by not using .lock anymore. But still, we want to improve our code to run faster, right? So the next problem is, probably inside this function. So this function is taking up 22 seconds, and if we can do this a lot quicker, then we could further save time. So let's just go to compute meta info, right? So let's go inside here, inside the utility file. I believe that's where our code is for compute meta info. So okay, but we don't if you just look at this code, I can't tell you exactly where it is slow. All we know is that there is some function call inside compute meta info, and this whole thing takes about 22 seconds, but maybe it's happening inside pre-compute, or maybe happening inside here. Although the pre-compute function doesn't come up inside any of these rows, so perhaps we can suspect that these two function calls are pretty fast, and somewhere inside here is the performance bottleneck, right? So you want to be able to take a deeper look at this particular function and see where the performance bottleneck, or see which line is the problematic one. Okay, so that's reasonable. In order to do that, we're going to introduce another tool called a line profiler. Okay, and in order to do that, you basically need to go into Python, and then you need to install line profiler, and this will give us a more granular detail about how the profile, about how long the profile, about how long the function, well, which lines take the longest to run inside the function. So you can of course look for it, line profiler in Python, and there should be plenty of resources online for you to understand how this works. So we're not going to go into the intimate details, but we encourage you to check this code out. Okay. In order to use the line profiler, I think we don't have to import anything. We can just do add profile here, and then when we run the code, I think we do. Wait, sorry, do we have it here? Line profiler. Do you have it? I think we make a function call like this, m turn prof, and then we say we want a verbose output to main.py. So let's try this, and this should work. Okay, so this is not important. That will probably be okay. So let's just let the code run. We're doing line by line profiling, so I think this will take even longer than the C profiler, but we get more detailed output, so that's good, right? Okay, so we look at this line, and very interestingly, we get this line. So let's copy and then put that inside of here. So this is our function output. Well, unfortunately, okay, you can see that basically 90% of the time was spent inside this very innocent looking line of code, which is, that's very good, right? So the power of this line profiler is that we can see precisely which lines are taking very long. So imagine you thought that this was the problem, right? Or any other lines were the problem. And then if you go ahead and try to improve those lines of code, what's going to happen is even if you can squeeze this down to virtually 0 seconds, the function call is still going to take almost the exact same amount of time. So you really want to be attacking the source of the problem, right? Which is this line and quite possibly this line. So, okay, we have to go through this. Okay. So let's just go inside here, and something inside here is taking very long to something here is taking very long. So what is happening inside this line that is causing us to run for so long? To do that, let's say we do is any1, and then we're taking the same, and we, instead of using a lambda function, let's just say we do exactly that. And then we can go in here and we will replace it with this, and we will take this. So that's pretty good. Now let's try it again. So what happens is, let's try print x, and then let's print the type of x. So we know what the rolling thing does, right? It goes 5 entries by 5 entries and see if any of the sample is set to true. So let's disable this for a moment, and then let's just call that without the profiler. So let's take a look at what this does. So sorry, let's let it pause. So we can see that we'll get statements like this, and we always get a pandas series. Now, let me explain a little concept here about the pandas internal implementation. So, by the way, different versions of pandas implements things a little bit differently. So it might be true, but depending on your pandas version, the internal implementation might be a bit different. So you should take whatever I'm saying with a pinch of salt. But basically, when we have a pandas series and then we call .rolling, so you're making this 5 entries each, and these are 5 entries each, right? But every time we do .rolling, then say we do .apply lambda, what is happening behind the scenes is that it's creating a new pandas series consisting of these 5 entries. So essentially, if you have about 200 rows, then you are basically creating about 200 new pandas series, right? And that is going to be very costly because you have to go and create a new Python object, allocate it to memory, and memory allocation is expensive to do because you have to talk to the kernel, and it makes the operating system will clear out memory and things like that. So, but the thing is, we don't need to do any of that, right? These elements are already inside the data is already inside memory. We don't need to create a new pandas series. Okay, we can just do away with all of that, and we can work directly on this. So we can somewhat have like a view on it, right? So we can just like take a peek at these 5 entries, and we can move down entry by entry to create like a sliding window without having to create anything new. So that's where the performance issue is coming from. Okay, so I hope that sort of makes sense. So how do we prevent the creation of new Python objects? Well, that's easy. All we have to do is try raw equals true. So let's try this statement. Okay. You can see we are basically referencing the underlying NumPy array. So that is useful. So okay, let's see what are the performance improvements, right? So well, let's go back to main. Let's run this code without the raw. So we're just going through the pandas series. We know that this statement is taking very long. This particular statement is taking quite long. Okay, so this statement will take us about, it should be slightly faster than this because we already changed the dot at everywhere else. So, sorry, I mean it should be faster than this. So okay, this is the actual runtime, assuming we did this change everywhere in the code. Okay, so let's just replace this, and let's see what happens if we prevent the creation of new panda series every time we iterate through. So okay, let's try to run this code and see whether our code runs faster. Indeed, our code runtime actually changes by like half. So actually, like half the execution time was used in creating the panda series, which is kind of ridiculous, right? When you look at the original problem, and you would think that okay, like at least 80% of the time will be done doing this mathematical operations and doing this mathematical operations and then making doing this sort of mathematics. But it turns out that actually half of the time was spent in this ridiculous statement. So this is why profiling is so important, because now you can focus on the right areas of the code to attack. So now that's certainly useful. So let's give that a record. So the changes that we made was to go from go from the apply and then raw equals to false, and what we did was to change this to true. And of course, pandas is not so stupid. There is a reason why they prevent you from accessing the underlying array, because they want to protect you from changing the underlying data, right? Because imagine you're working on the underlying memory, you're working on the underlying places in the memory, and you go in and you make some changes to the code logic. Then, for example, inside here, you do like, I don't know, you can make some changes to the variable, changes to the NumPy array, and then you will basically be changing the contents of the function. And apply is not meant to change the internal, the original copy of the data frame. So they're sort of protecting you. But of course, if you know that your access patterns are going to be safe, you can bypass these kinds of safety checks to arrive at that. So that's not too bad, right? We're running the same code that took about 6 minutes, right? Which is quite ridiculous. And then now you're running it at 10 seconds. So you basically have a 36 times speed up in the code for very minimal changes, right? You really didn't do much, but by understanding how the code works and understanding how the function calls works and the internal implementation of the panda series, you can then improve your code so that it runs like orders of magnitudes faster.